Hello, everybody. Today we'll be talking about the paper How to Improve Deep Learning for Software Analytics, a case study with code smell detection. This paper was accepted at MSR this year. I'm Rahul Yadida from NC State. I'm a PhD student, and I co-authored this paper with Dr. Tim Menzies, who's also from NC State. To start off with, what are code smells, which is the case study we're looking at? So Beckett et al. Eloquently put this as certain structures in the code that suggest, or sometimes they scream for, the possibility of refactoring. So we'll be studying 4 different code smells today, which are essentially big no-nos that programmers should try to avoid. So one is feature envy, which is if a method in class A is using more data or more methods from class B than it is using of class A, then class A is envious of class B because that method is using so much from class B instead. Which is to say, this method may be better suited belonging to class B. In the large class scenario, you have a class that wants to do it all. It's a class that does too much and maybe should be broken up into smaller classes. The long method code smell is a long method, as the name suggests, where programmers can't figure out what that method does because it's so long and so complicated that it does too much. It's the method equivalent of the large class code smell. Finally, we're going to study the misplaced class code smell, where classes are misplaced. For example, in Java, you could have classes that are in the wrong package semantically. How do you generate data for such a task for code smell prediction? Well, we used Liu et al.'s data, and they did smell-induced refactoring. They took clean code, and they did refactoring to induce code smells. One such way to do that would be you take a method from one class and move it to another class, and that might induce feature envy. For more details, please see their paper at the bottom. Now, what's wrong with prior work? To do that, we first need to establish what the prior work is. And so to do that, we did a literature review, and we started with a seed. A seed paper is one that gives you a bunch of references. And so for that, we looked at Watson's PhD thesis. Next, we topped it up with our own search terms from Google Scholar, and these were our search terms. Finally, next, we filtered these. So our filter criteria were they have to be published in top venues. They have to have at least 10 sites per year, or they need to be published in the last 3 years. Or if not, then they have to be highly cited. More than 100 citations would be considered highly cited. Finally, we did backward snowballing as suggested by Walden, which is to say, if paper A cites paper B, then also include paper B in your list of papers, assuming it meets your filtration criteria. When we did this, we ended up with over 100 papers that did deep learning for software analytics. And we broke it down, we broke down the deep learners into several types, and we broke down the tasks that they were used for into several types. So we have sequential models, if you look at the bottom of the chart, we have sequential models, which are RNNs, LSTMs, transformers, and so on. We have convolutional models. We have embedding models. We have a subset of embedding models, which are Word2Vec, but we took them out separately because of how prominent Word2Vec on its own was. There are other networks that were custom designed, so we included them in other. And more importantly, there was also feedforward. These are 1980s style multi-layer perceptrons. And there were some others. Moving on to the rows, which are the different tasks, we grouped them into code synthesis, things like text to code. We also have language processing, which is natural language processing and programming language processing. We have code comprehension, things like code summarization tasks would belong here. And we have some other tasks. We notice there's a heavy skew towards code synthesis and the use of sequential and convolutional models. These seem to be the majority of use in deep learners. Now, on its own, they're fine. They're pretty effective learners, but the problem with that is that they're slow, and sometimes they need very expensive hardware to run. So you might need modern GPUs, which some companies may not want to do. They may be reluctant to do so. And so you want to use simpler alternatives like feedforward networks, which have like 1,000 times less parameters than, say, a modern convolutional or sequential network. A modern transformer network, for example, can have hundreds of millions of parameters. So we want to use feedforward networks, and we want to do better. And how do we do that? So that's the problem with prior work. The problem with prior work is that they're using overly complex networks, and they may not have fully tested out simpler alternatives such as feedforward networks. Now, on their own, feedforward networks may not work particularly well, but it turns out with some clever pre-processing, you can do extremely well. And one such thing is the GHOST paper published by me and Dr. Menzies. And so essentially this figure here shows you how fuzzy sampling works. So consider the extremely clean dataset, the MOONS dataset from sklearn. And so you have two classes here, and assume that the yellow class is the minority class. You have a class imbalance issue, and the yellow class is the minority class. So after fuzzy sampling, you get the middle diagram, which is to say you have these points surrounding the original points. You also have more points in the original, where the original points lie, hence they're darker. Now, in the GHOST paper, it turns out that they use fuzzy sampling twice. So they do fuzzy sampling once for the minority class, and then they do fuzzy sampling twice for the majority class. Remember that fuzzy sampling reverses the class imbalance, and so if you do it the second time, it now recognizes the original majority class, which is the purple class, as a minority, because it's now the minority after the first fuzzy sampling. And so now in the second fuzzy sampling step, it's applied to the purple class. And so a similar pattern emerges where you have points surrounding each of the original points, and the original points, that curve becomes thicker because there are now multiple points placed there as well. Finally, in the GHOST paper, they use SMOTE, and they fix the class imbalance issue, which is caused by the second fuzzy sampling. For more details, I suggest you look at their paper on the value of oversampling for deep learning and software defect prediction. It was published at TSE last year. But after applying all their steps, you get the final figure. That's the rightmost figure here. And what you see is you have points surrounding each of the data points. Why is this beneficial? It turns out that if you do this, then it pushes the decision boundary of the learner away from the data points. And that's a good thing to have. That's a good property to have. Why is that? So you consider a test sample that comes in and is very close to the original training sample. But consider that the decision boundary of the learner divides them. And so this test sample, which is actually the same class as the training sample is close to, it has been misclassified. This occurs quite frequently, especially if you have a class imbalance issue. And so by adding points around these original points, as is done over here, this decision boundary is now pushed away. And this reduces the misclassification. So the GHOST paper, published at TSE last year, suggested that you use fuzzy sampling twice, once for the minority and once for the majority class, followed by SMOTE, and also use hyperparameter optimization, that is to find good configurations for the deep learner, the feed-forward networks, and they also use something called weighted loss functions, which we won't go into. So, okay, we have this promising approach that was initially applied for defect prediction, but does it work for code smell detection? And it turns out it does. If you look at the 4 code smells that we've taken, on feature envy, it does astonishingly well. We have 99 plus AUCs across the board. It's also doing well in large class and misplaced class, but it's not doing so well compared to the prior state of the art in long method. Why is that? It turns out that for long method, the prior state of the art also uses feed-forward networks. And so you have this situation where feed-forward networks are pitted against other feed-forward networks, and so it's less obvious which is the winner. But for the other 3 cases where the prior state of the art used more complex learners, the R feed-forward learners with the GHOST system, that is with fuzzy sampling and the hyperparameter optimization, was clearly better. What lessons can we learn from this? Simpler learners with adequate pre-processing, such as fuzzy sampling and SMOTE, can outperform more complex learners and do it faster. You may be able to do this on commodity hardware instead of requiring high-end GPUs for the computation. We want to try simpler baselines before moving to more complex learners, so that you reduce the amount of computation you need to perform. And my personal favorite lesson learned is to use GHOST as one such baseline. Thank you for your attention. You can find our paper on using GHOST for code smell detection at the first link. The second link is a demo of fuzzy sampling. These slides are available online at the third link, and you can contact us at either of the emails in the last line. Have a good day.